Good afternoon, everybody. My name is Jan Peeters. I'm founder, CTO of InfraCore company, so founder of FiberCore Europe. And it's my pleasure this afternoon to introduce you to our InfraCore technology. I'd like to start with this. What is the link between these pictures? You see scale-like structures, you see plate-like structures in nature with this, bridges, log gates, heavy-duty structures and infrastructure. The link between them, of course, is our InfraCore technology, and that is a novel way to make robust sandwich-like plates which are extremely damage-resistant. We've developed this technology in order to be able to use fiber-reinforced thermoplastic thermoset materials in infrastructure. But once we developed the techniques, we realized that it's much wider applicable. First of all, I'd like to explain a little bit what the technology is. The basic concept behind it is that if you want to use fiber-reinforced polymers in infrastructure, these materials must be robust. They must be damage tolerant. And of course, they should be price competitive. We're competing against concrete and steel, even wood. To explain, first of all, I'd like to set out a problem. I once designed my very first bridge as a classic sandwich structure, and I got a response from the Ministry of Transportation in Holland that it cannot be done. And there's a problem to be solved, and that is the skin core debonding problem and delamination. That's actually the Achilles heel of FRP structure. So if you have a sandwich structure, this is known, you drop a hard object on it, the core will crush, the skin is elastic, it will bounce back, and you get a skin core debonding. Very hard to prevent that. Normally that's not much of a problem, but when you start rolling wheels across a delamination like that, or debonding like that, you'll end up with a catastrophic failure in your bridge. So that's not acceptable as the backbone of an infrastructure product which should last for 100 years. There are alternatives, of course, to make a beam plate-like structure. You can take some protrusion panels or beams next to each other, but when you hit them, you get a very high risk of debonding between the flanges and the web. So that is not a robust solution. We talked about the sandwich structure is not a robust solution. Alternative could be a multi-box beam. So these are beams fully wrapped and then bonded together. When you hit that, your fracture surface, which is unimpeded by fibers, will be in vertical direction, so your bridge can split. That is not a solution. You can combine a classic sandwich with a multi-beam, get a combination, but actually what you do, you combine two fracture modes. So that is not a solution. We have a solution in which we made a box beam, InfraCore box beam, in which you can get damage, but you will not be able to take away material from your bridge. So the load carrying capacity remains intact. To explain a little bit more, we'll just look at a model bridge, and we're going to look a little bit at the beginning of a bridge, so this box, and look at the Y direction. That's the span direction of the bridge. So assume that we will make a bridge consisting of steel beams. This is steel beams. We have two flanges. We have the web. We're going to play a little bit with the beam. This is still a beam. It's still two flanges and a web. And if we then reduce the thickness, we still have a steel beam, but it's a thin Z-shaped steel beam. Well, then we make a switch as a thought model to a composite material. So assume that you were to make Z-shaped beams with a plus or minus 45 fiber direction going continuously from one part to the other. We can add some unidirectional fibers on the top and the lower flange in order to get some extra stiffness in span direction. The span direction is in Y direction. You can add some fibers in thickness direction to carry the wheel load a little bit better. And then you can combine it. This is essentially what InfraCore is. So what you have is a multitude of Z-shaped beams, almost independent beams. But what happens if you hit a structure like this? So if we drop a weight on our structure, we are not independent for delamination. We can also get in the delamination. But this delamination is only a local debonding between two beams which are essentially independent from one another. So it's a local phenomenon. And if you then start running wheels over it, what you will see is that because those two beams next to each other do not exchange much shear load, delamination between them stays stable. It doesn't grow. And that is the essence of what we do. So we do not get a skin core debonding because the connection to the core remains intact, even if you damage the interface a little bit here by an indentation. The interface essentially stays intact. You cannot take away material from the top, and you have no damage growth. Well, there are some options we have. You have in the core, we could put a foam block. The foam does not have a structural load function. You can add some cross webs in order to improve the shear load in cross direction. And you see some other variants, even the massive blocks. We use this solid blocks of FRP in locations where you have to reduce high local loads, for instance, bolted joints or something like that. Well, what does it look like in reality? This is a photograph on an actual InfraCore bridge deck. It's a tiny deck. It's 50 millimeters roughly. But what I've sketched here is that this dimension, so the depth of the structure, can be between 50 and 1.5 meters. So we talk about serious depth of the sandwich structure. The thickness of the skins, here it's something like 12 millimeters. We can choose somewhere between reasonably 1 millimeters and 100 millimeters, 10 centimeters. And the core block, so the width of the blocks here is typically between 50 millimeters and 250 millimeters. If you look closely, you can see the Z layers here. Oh, the Z layers running here, jump to the other side and they continue here. And if you look at the scale, you would see that the fibers which are here in the underlayer, they will step up a little bit and they end up in the top skin something like 50 centimeters to the right. And this layer will end up in the skin somewhere 50 centimeters to the left. Well, that is how it looks like. Well, what is the strength of the technology? We managed to combine the good properties of sandwich structures and multi-beams without the drawbacks. That's essentially what we have. We have a structure that is less vulnerable and it is cost competitive directly. And that makes this technology the technology of choice for robust heavy-duty applications like bridges and lock gates. What is interesting, this is a little bit of a sidestep, is that actually if you look at the skin of InfraCore itself, that is a new category of materials. So we actually invented a new material. We call that oblique layered materials. And then if you start looking around you, you see that there's a lot of parallels in nature. And in nature, we call them oblique layered structures. And that's now we're back at our first slide. Now you know, the first sheet, you know what the link is between them. So these are all oblique layered structures in nature. And you can find it everywhere in nature, in an artichoke, even in the nautilus, the tail of a lobster, even in the flesh of a salmon. So it's everywhere. And actually, if you look at what do we do? If you assume that we take a pangolin, which is flexible, it has its scales, its plates for flexibility in order to grow. In our case, what we would do, we would add polyester, dip the pangolin in the polyester, and then we let it cure, and then we have an InfraCore pangolin. That's the idea. So it's a solidified plate-like structure. And if you were to break open the connections by delamination, for instance, you still have the consistency of the base structure itself. So that is the damage robustness which we built into the structure. And what is a nice concept is actually evolution came up after 3.5 billion years with oblique layered structure. So the basic concept should be okay, and that's what we're using. This is what it looks like, oblique layered materials in paper models. That's the skin. And there are two variants of the technology. There's a Z variant of the technology, and you can make your webs in a truss-like structure or straight, or in a U-shaped variant. Once again, straight or trusses. And this obliqueness layer, that is something you will find in the skins of all our materials. We even adapted the classical laminate theory for that, because the classical laminate theory does not has no facility to account for out of the plane tilt of the layers. So together with a student, we developed an extension on the classical laminate theory to incorporate that. The technology is patented. We have 160 patents in 10 families, and licenses are available. The technology covers, let's say, the way of folding the fabric, but also the molding technology, the injection technology, the applications. So how and where to use the technology? What we would like to do, we would like to see that we develop together with you new product market combinations. And once we see a sensible application, we will help you to develop your InfraCore application. And the license options are then that you could apply for a pre-license just to assess the technology, play with it, get a feel if it works for your application. If so, you can switch to a development application to go a step further, and you end up with a production license. There are two variants. We could still engineer and pre-produce the parts of the final composition, and the injection is done by you somewhere in the world. Or you take a full license where you have the whole spectrum from engineering up to production and installation. So the sectors we are servicing today are these: infrastructure mainly, also marine, very upcoming, new energy, and here, of course, whatever you might think of. And these are the unique selling points: cost competitive, robust, steel hybrid combination joints are developed. Well, just to end up with some examples, these are small-scale bridges. We developed something like 1,200 bridges already, locates, very nice shapes. This is the first 60-ton traffic bridge in Holland. So the whole plate, that thickness of roughly 90 millimeters, 90 centimeters, that is one full injection of InfraCore. So we like to inject big structures in single shots. 142-meter bridge deck. On the floor level, there is no steel-steel connection. There's only an InfraCore deck. And this is a very lightweight structure across a highway in Holland. This is a typical bridge deck. Once again, a single injection, and the thickness is the full thickness is an InfraCore structure. Another one even bigger. This is one of the biggest injections we did. This is 21 tons of polyester resin injected in a single shot. And in this case, this bridge carries 60-ton traffic load on a line support here, a line support this. The steel is only for the movement of the bridge itself. Even bigger, over the diagonal, 29 meters, another bridge deck, 60-ton traffic. Lock gates, you see these are big lock gates, actually the biggest lock gates at the moment in the world. Look at the people down there. These are very big doors, 13 meters high. Here you can see them in operation. So the water level here is something like 8 meters, 9 meters, which has to be contained. Fenders are being developed, and this is another development where we make U-shaped InfraCore airfoil. So this is the sketch. This is the first extension, and this is the first prototype, and we're trying to develop it right now for this airborne wind energy system, where the mid-section of the wing is now being developed as a U-shaped InfraCore section. Within the project of Ramses for Becker Marine Systems, we developed a rudder flap. This is a ship rudder of a very big 18,000-ton container ship. You see here that a rudder flap like that. Look at the guy. That is a serious structure. It is roughly the size of the lock gates we saw in the previous slide. And we made a scaled-down version for it, 1/6, using the InfraCore technology. You can see here we used horizontal webs in the sections here, vertical webs in that section, massive parts or solid parts in there, and this is also a full solid part. All once again injected in one shot, and it has been tested, proof tested, and it proved sufficiently strong, more than enough. Approval in principle is pending for this application. Within the same project for Ramses, for Meyer Werf, we have been looking at interior paneling. These are the panels which would define a cabin. And we've done the fire testing, and we now have an FRD 60 bulkhead fire classification on InfraCore. But what is interesting, when you expose InfraCore to fire, you can burn away the resin, but because the fabrics are still nicely woven through the core, you do not lose your fabrics. The fabrics will stay in place, so you will always retain some residual strength even after exposure to fire. Within Ramses, we developed parts, technologies for an 85-meter ship, and that has been done mostly with Damen shipyards in the Netherlands. that the Ramses project has a few stages. You begin at laminate level, you study joints, a test box, and finally a full-scale demonstrator. I'll briefly show something of it. So this is the cross-section of the ship, and we've been focusing on developing these joints. And these are joints, InfraCore joints, to, in this case, a classic sandwich laminate. And as you can see, we developed flexible joints with which we can absorb some bending stiffness. These are some designs. And this is the classical trajectory which you run through from concept to cut models to a finite element model and up to the final testing which we did. And we certified these tests, or these joints, with a safety factor between 6 and 8. One step up, the use of the actual joints, so the joints which have been developed are used in this application, which is a full-scale model of a ship. So the laminate, the deck thickness is realistic. The side panels represent the hull. These are realistic. The joints are scale 1:1. The bulkheads are scale 1:1. What you see here is a four-point load test where we try to break the ship. So this is simulation of hogging and sagging deformations. And the test has resulted in an 800-ton load, which was carried by this sample, which is an extreme load. And in this references, you can look at the films which are associated with that. Then within the same project, we had to prove that we can indeed inject, for instance, a hull in a single shot injection. And this is the first test for a vertical injection, 6 meters high. We were successful in filling that. And once again, we did that live during a project demonstration event, a live demonstration of an actual injection of an InfraCore skin. And what you can see here is the typical injection. You see that we fill the laminate in thickness direction with injection points. And knowing that this works, the 6 meter high injection tells us that we can inject an 85-meter ship in a single shot. We know how long it will take. We know that the injection will work. And this is the demonstrator which was built. So the hull section, the decks were developed by us. And on this demonstrator, there was an impulse test, so an impact test on both the top deck and the hull section. And we also did a fire test on the top deck. And we succeeded with flying colors. One of the more recent developments is the development of inland ships. So these are long ships, 76 meters, 110 meters. They've been developed on paper, and the developments show that we can get substantial weight reductions for this inland shipping, which will allow this kind of ship to reach higher up the river or carry more loads. It's a very interesting development. And then finally, an offshore application, just a sketch. There's a lot of offshore wind turbines, which all have a service platform like that in steel. And if you have a little scratch there, you have to send the ship to repair the damage before you get corrosion. The concept of an InfraCore panel or service deck could be that you have a maintenance-free structure, which you build it once and you use it afterward without any service needed. Okay, so that's an overview where we stand. So I showed you some applications from the infrastructure, from marine, from new energy. We have applications in the other applications. There's no time to further discuss. We would be very interested to hear what your ideas are, where you could use this technology. Once again, how could we do that? Finally, our objective is to work it towards a license with you. That is what I would like to tell you.